Hi everyone, Dr. Daniel Hampikian here from Boise State University. I'm a professor for the GIM department, or Games Interactive Media and Mobile Technology department at BSU, and I teach game development and web development and app development, a lot of development. And this is a video primarily for my students, but I wanted to share it with the world, where I'm just gonna explain my understanding of artificial intelligence and machine learning, and I hope you enjoy it. We'll go from the theory to some actual concrete examples, some Python examples, and we'll go through some examples using some more advanced APIs for machine learning, like TensorFlow and Keras. So if you've heard of those, we'll go through those a bit too. And really, I just want to go through some Python basics and just show what a neural network would look like in a very simple form, and then show how it gets more complex. And my goal is to get to a point where the next video, in a follow-up video, where we go through Unity's machine learning agents. So the Unity game engine released a while ago, but I've kept on developing it. A just amazing library called ML Agents, where they have reinforcement learning agents inside of a video game making system. And this is just very, very cool technology, very cool software. It's really amazing what's going on there, and in order to really understand just the complexity and the power of what they've developed, I think it's very beneficial, and it's just beneficial in general to have a good understanding of artificial intelligence from an abstract perspective and from a hands-on perspective. So that's what this tutorial, video, lecture, whatever, is all about, and I hope you enjoy it. So let's get started. Artificial intelligence, that defines, it's a field, right? And it basically defines intelligence demonstrated by machines that would normally be associated with natural intelligence. So that's usually things like cognitive tasks like problem solving, classification, and learning. I like to think of artificial intelligence, if you think of it as a field, it's a field that combines a lot of other fields. So philosophers like me, developers, psychologists, computer scientists, and neuroscientists, and even economists are involved in the field of AI. And the general idea is that artificial intelligence is just a range of activities where a machine or a digital software is trying to solve a problem or given a goal by a human, or maybe by another machine, but a goal that would normally be associated with a human, like play chess here, predict real estate prices there. Machine learning, artificial intelligence has been around a while, but machine learning really took off and continues to take off and just be a huge field to go into, and it's a subsection of AI that's concerned with programs that can basically learn from input and output and modify their structure, so modify their internal weightings of their algorithms to be able to solve a problem or accomplish some cognitive task. So let's take a closer look at what machine learning is. That's what we'll be talking about here, and that's making neural nets, and deep learning is all part of machine learning. There are many, so there's a big difference between typical software and machine learning software, because machine learning software has this flexibility in it where parts of it can change over time as it learns from the input and from the output that it produces, and then the feedback it receives based on that output. So there's this flexibility, this internal flexibility especially in neural nets and machine learning, that you don't see in a lot of software. There are many techniques of machine learning. So regression, classification, clustering, and dimensionality reduction are all techniques different than neural nets and deep learning, which we'll be focusing on in this lecture. But they're usually done in conjunction with neural nets and deep learning, and often prior to putting some data into a neural net. And natural language processing is another technique of machine learning. So we're going to be talking about one type of machine learning. So the types of tasks, the goals that machine learning algorithms are given are broken into supervised, unsupervised, semi-supervised, and reinforcement. Now, supervised tasks are probably the most common in machine learning. And this is where a human, or many humans in most cases, have gone through and labeled a whole bunch of data. And so they might have labeled, for example, data that signals someone has heart disease. So doctors might have done this painstakingly, logged it into a database. Researchers might have made that data, compressed it, made it numerical so that a machine learning algorithm can train on it. And then as it trains on it, the accuracy of its predictions, does this person have a heart disease, based on this data, are assessed, because those predictions, we already know if a person has heart disease or not. Some human has gone through and labeled all those cases and diagnosed the person. So because we know the answer, the machine learning can be trained in a very supervised way. Does it make sense? So the supervision is prior to the machine learning algorithm training on some data. We already know the answer, and then we give it new data to test it. But even that data we have labeled. Then there's unsupervised learning, where the data isn't really labeled. We don't really know what associations we're looking at. We just feed a neural net or something like that a whole bunch of data, and we ask it to come up with associations between that data that we weren't aware of. There's semi-supervised learning, which is kind of a combination of the two. Some of the data is labeled and some of it is not. And then the most exciting type of machine learning task is reinforcement learning. This is where you don't actually have the best answer, the classification or the prediction is not there. Instead, an agent learns over time by trying things and getting rewarded for things that bring it closer to an objective that you give it. So this is a way that a lot of sophisticated machine learning agents that play games like Go and initially chess and the Atari games that are played in Open Gym AI, and this is actually the type of learning that we'll be talking about when we talk about in the follow-up video, Unity and machine learning agents, which use reinforcement learning. And basically the agent learns over time. You just give it a goal, and if it doesn't get to that goal, it gets a punishment, like a -1 kind of thing. If it does get to that goal, it gets +1. If it does actions that bring it closer, it gets +0.1 or something. Actions that bring it further, -1. Then over time, it's more complicated than that, but over time it learns the best way that it can determine, given the data that it's given and its algorithms, to get to a goal. And that's a very cool kind of learning, because the parameters of what's correct aren't really set. Instead, there's a goal, and we leave the means to get to that goal open. So that's where we're trying to get to. Very complicated form of machine learning from a development perspective is reinforcement learning. And finally, there's artificial neural networks, which is a subsection of machine learning. A very exciting subsection where a lot of cool things are happening. And this is a type of machine learning that uses the fundamental structure of a neuron, or perceptron, loosely modeled after the human brain's neuron. So neural nets consist of sometimes nested layers of neurons that accept numeric input and produce numeric output, usually changing their internal statistical properties to better accomplish a classification or a prediction task over many iterations of training. So a lot of data manipulation has to happen prior to a neural network. The structure of a neural network depends. We'll talk about that in a second. Actually, I want to bounce out here and just go through a little bit of what I mean by a neural network being based off of a human neuron. So they were initially called perceptrons when neural networks were developed, but let's talk about the structure. The structure of a neural network is very similar in some ways to a human neuron, human brain, where you have layers of neurons that interact with each other. So let's talk about the human neuron. I think it's very worthwhile towards understanding artificial intelligence if you think of it as a way to also understand human intelligence, because in order to make something, you have to understand what that thing is before you make it. So making something intelligent teaches us about our own intelligence. And so if we think about a human neuron, it's basically just a cell with two parts of interest to us right now. It has many more parts than that. But, the synapses and the axion. And the synapses, the cell itself responds to electrical stimulation through an electrochemical pulse signal at a certain threshold of stimulation. Let's see if we have a human neuron here. Okay, so if you think of this as just a map of a human neuron, basically you have information coming in, right? And then at a certain level of electrical stimulation, that neuron, sometimes people call it fires. So there's an ionization basically that happens, and a chemical change happens, and then the neuron produces a little electrical signal. Passes that on to the billions of other neurons. So there's about 100 billion neurons organized into like three main areas of the brain: the forebrain, midbrain, hindbrain. And they form a dense interconnected set of exciting signals. There's an electrical storm going on every second that you're alive in your brain. And that is excitation signals of electricity that depend on the strength of the input and the internal structure of the nerve cell. But basically, this is what's important for us. An artificial neuron produces inputs and outputs that depend on the activation function, so the signals coming in, and the weighted sum of the inputs. So let's take a look at that neuron again. And these W's here are like the weights. So you could think of this as the strength of the electrical signal for a human neuron. But for us, these can just be numbers, right? If we're making an artificial neuron, we just need numbers for the weights. You can think of this as like in college courses, oftentimes in the syllabus, professor says, that I used to do this, so that the final exam is worth 40% of the grade, right? And homework is worth 10% of the grade, and whatever. So the weight of the final exam, if you got a 90 on it, you multiply that times 0.4, right? And the weight of the homework, if you got 100 on that, you multiply that times 0.1 because it's 10%. So these are statistical weights, and all of the percentages, then you add those together to get the final grade. And that model of multiplying weights and then adding them together is really the core of a neuron in a neural network. That's what goes on. These weights come in, and the weights change over time, right, based on stochastic gradients and back propagation. But essentially, you have these weights, and then the weights hit an activation function, which is just a formula that says, what kind of output should you send to the other neurons? That's it. It gets a lot more complicated, but the core of a neural network is that. Okay. So, So, for example, we have just a blank activation function here, but you can see the sum of the weights plus whatever bias we associate. So sometimes you can bump these up or down with a bias neuron, and that's what gets output, and the output gets sent to all the other neurons. that's the basics of a neural network. So neural networks are, like I said, there'll be a stack of neurons, right? And so some input goes into a stack of neurons, and then those all go into a single output. Now, deep learning or deep neural networks, it means that the stack of neurons, there's more than one, right? So there's more than one layers of neurons that have their own weights and have their activation functions on top of each other. And the top layer is feeding into the next layer, which is feeding into the next layer. And in general, the more layers of the neural network you have, the more complex features it can respond to. So for something like video categorization, you need quite a few layers. For something like predicting truth values of logical statements, one layer will suffice. So I have some diagrams of this. First, here's a very, very basic diagram of a neuron. Input comes in, the weighting is applied. The neuron gathers the weights and puts them into an activation function and then sends an output. Layers. So this is actually a deep neural net. It's a very simple deep neural net, but it has more than one layer, right? So some more complex neural nets might have hundreds of layers and hundreds of neurons per layer, maybe thousands. The input layer. The input layer is just raw data that comes in. It doesn't modify the data in any way, and then you have a bias neuron sometimes, and that'll shift the data up the same amount for every new neuron. A hidden layer is where the actual transformation happens with the weights, and then the output layer, they all have to give usually a single output. Sometimes you have an output with maybe a percentage of confidence in that if it's a categorization task. And that's it. So it's, the information flow is a lot like a human neural network. That's what we're looking at, a human neuron here kind of in the background. And with the dendrites, the axion. But in theory, it's nice to compare these, but there are quite a lot of complicated things that this very simple statistical algorithm leaves out, right? So it's just good to keep that in mind, that we've drastically simplified and just gathered the informational flow of one type of thing, the electrical signal, because it's very much like binary, and translated that into an algorithm when we design a neural network. I do want to talk briefly about the data manipulation questions. So the power of an artificial neural network depends on two factors with sub factors. So the data manipulation itself, so that just means how is the data prepared before you give it to a neural network, and then what do you conclude from the output data, and then the structure of the artificial neural network. So the complexity, how many layers are there, how many, what type of hyperparameters have you put on it, what type of extra algorithms are going on to modify these weights over time, the depth and the breadth of the artificial neural network. So the depth is how many layers, the breadth is how many neurons per layer. The internal structure of individual neurons can be more or less complex. So neurons, for example, with LTSM neural networks can have memory, right? They can remember their last state and make different choices about their weightings depending on their last state and their current state. And the way that neurons can change over time too can vary. So biased neurons, of course, never change, whereas LTSM neurons can change pretty rapidly. With data manipulation, this is really a huge part of machine learning. The data has to be prepared, and you have to gather the right data. So they have to ask a lot of questions. You have to reduce any kind of input to a number or series of numbers, so the neural net can learn from it. You have to be able to reverse that process and get predictions or classifications. And understanding the problems, you have to ask at least these questions, but probably a lot more. So what am I trying to categorize or predict? What are the causal factors surrounding this phenomenon? What data associated with these causal factors should be correlated with this? How might I reduce or expand these features to more relevant ones? And what sources or techniques can I use to objectively establish the relevancy of features to the problem? How can I pre-process these features to make them numeric neural net input? So think about if you wanted to predict the stock market. You'd have to know quite a bit about the stock market and to determine that maybe I need to pay attention to things like the other stocks in other countries, right? The economies of other countries. Maybe I need to pay attention to the media, to these hedge funds, what they're doing, right? These are all causal factors in the stock market and obviously I'm no genius at the stock market, but they're all, I assume, causal factors that surround the phenomenon that you would probably want to capture in the data that you're feeding into the neural net, and you would want to capture it in a way that makes it numerical. So all that happens in data science usually prior to the neural network itself. And I'll put this in the resources for this video, but there's a nice example here of what types of questions you would ask if you wanted to make a neural net to predict real estate prices, which was actually done in the Kaggle competition, where it's been done many times actually, but yeah, I'll put that in the resources. But just a lot of questions where you expand. All right, what features do I think are relevant here? What's the most relevant features to understand real estate prices? So it's just a good example of that. All right. Let's go inside a neural network, and this is the point where we'll start doing some code examples as well. So let's do that. So here's a little diagram of a neural network, and of course you have input neurons. So an input layer, that's just a layer of neurons that just passes the data on. It doesn't apply any operations or signals or anything like that. But you need an input layer because you need to anticipate how many neurons are coming in, are going to receive data. Oh yeah. And a bias is neuron accepts no input but contributes a bias output to the next level. You can have biases at any layer, right? And it's going to add like a plus something or a minus something bias to, or a multiplication or division bias to all the weightings of data. A simple neuron, the most basic, is much like a human neuron. It takes inputs, applies a weighting to them, and an activation function to them, to the weightings, receives the weightings, and that activation function then passes output to a subset of neurons, or maybe all the neurons in the next layer. It's a very simple data structure, just weights and an activation function. As we saw before, weights look like this, right? And they're just statistical, probability weightings that you give input data. So weight represents the strength of the connection between units. If a weight from node 1 to node 2 has a greater magnitude, it means that the neuron 1 has greater influence over neuron 2. And a weight brings down the importance of the input value. Weights nearing 0 mean changing this input will not affect the output. So essentially takes the input kind of out of the picture for the next layer, and negative weights increase. Negative weights mean increasing this input will decrease the output. So the weights can be negative, they can be fractional. And we usually, the cool thing about neural networks is you don't have to worry about them. You can randomize them because that's what's going to learn over time. Neural networks, just their weights evolve over time, to learn the predictions that you want them to learn, or learn the categorizations that you want them to learn, just like the human brain. So you can initially just set them randomly, and that's the very kind of spooky thing about neural networks, is they change their weight and they actually get very, very good at some kinds of tasks, far better than a human in some cases. Activation functions are called things like Sigmoid, Relu, Celu, tanh. They're all just formulas, and what they do is they just take the weighted input. They take all the weighted input, and the sum of them usually, and then they do something with them. So Sigmoid function will squash the value of all the input to a range between 0 and 1. So kind of like a human neuron that only fires when it receives a certain level of excitation. If you have a neuron with a sigmoid activation function, it's just like that, right? At a certain level of inputs after they hit the weights, then it'll fire a 1. Otherwise, it'll fire a 0. Relu is another activation function that's more commonly used. And let's take a look at some of these. So what I'll do now is I'll switch to Google Colab, and Google Colab is a really cool way of running Python code right in your browser. So this is just a Python notebook that we're looking at, a .ipynb file. And if I type some Python code in here, and then hit Control Enter or click this little run button, it will actually run the Python code right in the browser. And the cool thing is we can run like complex TensorFlow neural nets in the browser as well as little strings that say hi. So what I want to do is I want to take a look. I want to just show an example of a very basic neural net without using TensorFlow or any of these huge libraries, APIs like Keras, and just show what it would look like in code without all that stuff. So first, and I also want to just kind of get you familiar with Python basics. But what we'll do is we'll look at the activation function, the weights, and how training would occur. We'll look at all that and how it would look in code instead of just talking about it abstractly. So I'm going to import some things in Python. I'm going to import random, and so this just means I want to use a library, right? I want to use a chunk of code that exists somewhere else in this very file here. I'm also going to import, and this is almost everywhere where you do machine learning, Numpy. I usually hear it called, and this is just a library. It's the main package for scientific computations in Python. It's like the major backbone of Python in machine learning. Numpy was so it just makes a lot of computations faster than they normally would be, and that's because of some things that don't really matter here, but basically, vectorizations that eliminates unnecessary loops in code structure. So we'll use that, and the other thing, I think that's all we actually need for this. So let's see, what should we do? So we'll make a simple feed-forward neural network that can be contrasted with backwards propagation neural networks. And when you have a neural network, usually you want to run it for more than one time. And so let's set a time. So if we want to set a variable in Python, we just do it like this. No need to declare a variable type. Most neural networks also have a learning rate. So let's set that to, I don't know, kind of a high value like 0.7 because I want this network to learn very fast. And then our weights, which are really the only part of a neural network that change over time. Like I said, they can be randomized. So we'll be random.random, random.random, and random.random. And then let's print that out. The weights before training. And we'll add in here a string of the weights. I'm going to run that and make sure everything imported okay. So those are the numbers we got that time. Just some floats between 0 and 1. And so the cool thing about neural networks is the only thing that's really going to change internally about their structure is, in this case and in most cases, is the weights. So the weights are the things that learn over time. That this is successful at predicting or categorizing. This is not important to predicting or categorizing. And oftentimes other things change, like the learning rate might go down over time, the alpha value might go up or down over time, but the weights are the main thing. In fact, you can think of a neural network as, mostly a collection of weights that are attached to a single node. So let's write a function now that defines our neural net. So to write a function in Python, you type def, and then you open your parentheses, and you type the parameters that you would want that function to take. So we'll have an input neuron 1, input neuron 2, and this is going to be a very basic neural network. Expected output, and then we want a semicolon there, and make sure that it's tabbed. All right. We'll do our output actual, which is going to be our input neuron times our weight at 0. So if we want to access this weight in this array, we do it like this with brackets, and what we're doing here for the output is we're just going to take the sum of all the input times the weights. So input neuron 2 plus weights at 1. And we can have a bias too, why not? So you saw that there were bias neurons. What you would do for that is just set a random or non-random bias that you can adjust to account for input. So why don't we bias the second neuron? And then we'll multiply the bias times the weights at 2, and so the bias won't change over time. And this needs to be times. Okay, so that's what we're gonna do. We're also going to we actually need another function here. So we need to write our activation function. So let's use the Sigmoid activation function because we're going to do a very simple task here. We'll apply Sigmoid activation, and what do we call that? Just X. And for that, all we need to do is return, this is the Sigmoid function, 1 over 1, and we just need NP. Basically the exponential of whatever we give it, and so we just give it the negative exponent of whatever we input. Yeah, okay. Finally, we need to calculate the error. So the error is going to be our expected output minus our output actual. And then what we'll do, so it's a very simple error measurement. What's the difference between what we expected when we're training the neural network and what we fed into the neural network and got out as a result of this calculation? Now we need to adjust the weights. And what we'll do is we'll add in the error and we'll multiply that times the input neuron at 1, and we'll also multiply that times the learning rate. And then I'm just going to copy this. We'll do that for all three of the weights, even the one affecting the bias neuron. And this is going to be bias. And this is going to be input neuron 2. And then let's write one more function here to handle our output so that we can, so we'll make a softmax calculation here, which is, again, just the straightforward exponent of that value, and then the expo sum, which will be the sum of NP exponent x, and we'll return the expo divided by expo sum. So when we feed in an array to this array of values, we'll get one value out, right, which will be the sum of the exponents, like that. Okay. So don't worry too much about that one. Let's train. So let's set up the actual training of the neural net now. So that's all the setup we need. Now, if we just do this, well, let me actually run it and see if we get an error. Okay, good. So now if we, let's just do a new block of code. It's kind of nice to classify these in blocks of code, and I want you to learn how to use Google Colab and use Python notebooks as well. And so let's write the actual training of the neural net now. So for I in, if I want to iterate through something a whole bunch of times, and epoch is defined up here as 500 epochs. So for 500 times is what I'm doing. It's a for loop in Python. We're going to call each time neural net, and we'll pass in weights. And we'll pass in 1, 1, 1. And we do have a reference to weights up here, right? Yeah. Okay, so we'll pass in weights for weights. Why don't we call this W so we're not confused about that? So we'll do W equals weights. And that's a nice way to make sure you pass a parameter like that. Then we'll pass in 1, 1, 1. And what we remember what this is the two input values are 1 and 1, and the expected output value is 1. And so what we're going to actually try to teach this neural net is logical OR, right? So or, so, you know, 1 true, 1 stands for true in this case, true or true statements are true. And then we'll do the same thing here. We'll do it 4 times. So each time the neural net has a chance to adjust the weights. Of all of the 500 times. A true or false statement, remember logical or, so if I say if it's raining or it's sunny and it happens to be sunny right now, or it happens to be raining right now, it's going to be true. So true or false statements are true. I hope that makes sense. I'm not really communicating that very clearly, but like logical or in the human semantics, if I say it is either noon or it is not noon, even though one of those two statements is false, the whole statement as a whole is true. And so that is what I'm trying to teach this neural net. So if we have where 1 stands for true and 0 stands for false. So if we have a 1 and a 1, if we have a 0 and a 1, same thing, right? That's also going to be true. It just means we have a false statement and conjoined with a true statement. So a false statement or a true statement, that's going to mean that the whole thing is true. And finally, if they're both false, is the only case in which logical or is in fact false. So the expected output in this case should be 0. All right. And then, so we have some visibility on this. Why don't we do if this I that we're using to iterate, modulo 200, if it's one of 200, if it divides evenly into 200, or by 200. If it's a 200, if it modulos into 200, so if it's at 200 or 400, in that case, actually let's do this by 100s. So every 100, that's what I'm trying to say, every 100 iterations, we will print out the weights. So that we can see them changing over time. We can see the neural network learning logical or, right? A human semantic concept and a logical concept. And then to test this, well, let's just run that so you can see. We get a positional argument by keyword. Okay, so let's not do this like that. Let's just oh, I shouldn't have adjusted this here. It's fine. Okay. Let's run this again. And run this again. Input neuron is not defined, so that should be an input neuron 1. Okay. One more time. This is the disadvantage of putting these in separate cells, is when I get an error, I have to bounce back. Base is not defined because I didn't spell it right. Alright, so I'm recompiling when I do that. And cool, okay. So we're starting to get some adjustments. You can see we have these initial values up here of 4, 0.4, 0.1, and 0.9. They start at 0.8, 0.3, and 0.2, and then adjust. This one adjusts up. This one adjusts not very much at all. So one thing we need to do is we need to apply this sigmoid activation function, because we're just adjusting the weights at this point. So what we'll do here is we will change the output actual, it's misspelled, to be equal to the input, or the apply sigmoid activation to output actual. The error is the expected output minus the output actual. Managed to misspell that twice. It's funny, I get to rely on Visual Studio so much that with its highlighting all my spelling errors, that what's going. Alright, so let's run that again. And run this again. There we go. That's a good change in, very kind of smooth change in learning. These two are increasing and this one is decreasing. So to see what these weights actually do, let's write another little function here. Let's test this with a we can just leave open. So if I want to like leave some input open, a while true x equals, and we'll turn whatever I put into input. So in Python, when you want input, you just use the input like this. You can put a message in there if you want. What I'm going to do is just leave a loop open at the end until I stop this from running. And what that input will do is it'll take two values for input. It'll make sure that they're integers, and then for the output, we'll do x times our new weights at 0 plus y times our weights at 1 plus our bias times weights at 2, and we'll print that output. We do have a binary active. We have a binary, so what we'll want to do is we'll want to do the Relu derivative activation function. So I'm going to just write two other functions here really quick. Softmax might work, but I wanted you to see Relu anyway, so let's do these two other functions. So for output, when we have binary classification, since we're choosing between two, the formula, the Relu activation, is going to be what'll give us a binary choice here between 1 and 0. So we'll do apply Relu and that'll take x, and it'll be if x is less than or equal to 0, then x equals 0. So that'll smooth out our large weight values. Otherwise, x equals 1, and then we'll just return x. And so for our output, we'll print the output before Relu. So you can see it, and then we'll apply the Relu. So output equals Relu This is really the Relu derivative, but that's okay. Output, you get the idea. We're flattening the data down to 0 or 1. And then we can, actually in this while loop, we'll still print x or y is output. So like true or false is true. True or true is true, and so on, right? So we should get this last value here, the logical or value. And yeah, okay, let's run that now. Let me run both of these actually. There's our weights before training. Here's our transformation of weights. And so now we can input maybe a 0 and a 1. And we get an error because I did something wrong. String must be, oh, I can't just print the output like that because it's not a string. So let me just take out the string here so we can still see it. Run this again. All right. So what did we do? 1 or 0 should be 1. Good. Okay. So it learned, and what it did is it flattened down this not 0 or less than 0 value to 1. If we do 0, 1, 0, which should be 0, we get a negative value because of the weighting. And if we do 1 and 1, we get a true value, which leaves 1, 0, 1, 0, and 1, which should be true still, so 1. And we get it. So we wrote and taught a neural network in just a few lines of code here. And we didn't use TensorFlow or anything like that. We just wrote our own neural network with some pretty simple Python. We didn't use a softmax, but we could have used a softmax instead of the Relu. Okay, so yeah, I hope that was helpful to you in understanding the basics of neural networks. It's going to get more complicated as I continue this video series, both on the Python side and because we'll start using TensorFlow and Keras, which will just automate a lot of this stuff and allow us to create densely connected neural networks with all kinds of things like alpha values and learning rates that vary over time, hyperparameters where we specify like the way that it'll learn, the type of neuron that we're going to use, whether they're going to drop out or not, right? And so it'll get much more complicated until we get to reinforcement learning, which is where I ultimately want to get to, which will be, we'll do it just in Python, and then we'll switch to the Unity game engine, which uses a Python in the background of its ML agents repo, just so that we understand what's going on. It's not magic, and we really appreciate the complexity and the power of what's there in the very beautiful thing that these developers have made in machine learning agents in Unity. And okay, so that was a very basic neural network. Let me see, what else did I want to talk about here? So we looked at the Relu and the Sigmoid activation functions. We used Relu on the very last, right? We used Relu right here as an activation function from the last layer of neurons to the output, and we used Sigmoid in our hidden layer. And I don't remember if I talked about this or not, but neural networks can get very complex. Their internal state can do things like hold on to their previous state, so they can have short-term memory or long-term memory, and they can then make up a recurrent neural network because the neurons link to neurons in layers that follow it, but also can loop back on themselves, or they can link to previous layers of neurons. So you can get more complex neural networks. The output neuron shapes the data, so we just saw that where I smashed the data into a 0 or a 1 because, so the program can evaluate itself. So we could have used the softmax function to ensure the probability of each classification. You saw what that looks like in code. I didn't actually wind up using that because we had a binary classification task. So once the network is set up, many of its properties are static. They don't change over time. The changes that happen to the input and output and the weights, that's where the changes happen. And they happen many, many times very rapidly, right? We did 500 iterations in less than a second. The only thing about the neural network that we really need to keep track of in many cases is the weights. And so the weights essentially are the neurons in the simplest kind of neural network. So this creates the ability of neural networks to do a thing called transfer learning, where in very complex neural networks, and we'll see an example of this maybe in this video, maybe in another, where if you've built a neural network that can do things like identify certain types of images, this exists, right? The weights and the architecture of that neural network are set up and just have to be recreated and applied to new images, new pictures, and the learning actually transfers because the weights record all the learning that has happened. So that is a very cool property of neural networks. Their knowledge is essentially immortal as long as the weight is changed. I don't think I have anything. Oh yeah, I do. Very important thing actually. So neural networks can get more complex, and deep neural networks often involve backpropagation, which is adjusting a neural network's weight during training, and it's usually the primary means by which that happens. We didn't actually do that. We had a feed-forward neural network. But if you're interested, well, this is already running kind of long, so I won't do a backpropagation by hand. But this happens automatically in TensorFlow and Keras with a certain setting. It works by calculating the weight change amount for every weight in the neural network, usually based on an error measurement with the expected output. The process is repeated for every iteration. Whoops. And how the weight change is calculated depends on the training algorithm. Classic backpropagation calculates the gradient for each weight in the neural network. So, with respect to the error function, okay. Usually you have many epochs per batch. So an epoch's a complete run through the data. And usually you don't have, we made a data set of just 4 arrays, but usually you're talking millions, billions of data arrays. And an epoch is a complete run through all of the data. And there are many epochs per batch. So a lot of times what you'll want to do to avoid localization is you'll run different batches and then compare the results of those batches with another algorithm. That's because you might get stuck in a local minima or a local maxima. So let's take a look at that picture. So if we're looking for categorization, you can see that maybe we want to get here, right? We want to get to this minimum, but we get stuck in this local minimum because the neural net knows that making errors in this side leads us further away from the goal. Making errors in this side leads us further away from the goal. So what we'll do is we'll divide that up into batches, and with the idea that one of those batches, one of those initial randomizations, will hit the actual sweet spot of accuracy for a prediction, or for a prediction or for categorization. It'll converge. And the other thing you can do to avoid local minima and maxima and get the actual goal that you're going for is you can use gradient and descent to optimize the weight. That's just another formula, a little bit of calculus. To do backpropagation, you just calculate the derivative of the loss function instead of, we looked at just the loss function, right? But you could calculate the derivative of that and then use that to adjust the weights propagating backwards. And the learning rate, of course, determines how quickly or how slowly you want to update the weight parameters. So you saw the role of the learning rate in that little piece of code I showed you, but basically it's going to determine how fast or slow those weights are going to change. All right. And that is inside of a neural network, both in code and in theory. Let me talk briefly about reinforcement learning. I'm going to do a follow-up video to this where we talk about it in more depth. But reinforcement learning involves agents, an environment, and a goal is how it's usually framed. And don't think too concretely about that. The agent is just a collection of code, as is the environment and the goal. But the overall AI of the agent learns over time by trying to get to the goal and going through many iterations. And every time it tries, if it gets the goal or gets closer to the goal, it receives rewards. When it gets further from the goal that you set for it or doesn't get to it, it gets punishments, which are, again, don't think too, it's very metaphorical, right? They're -1s and +1s, basically. And the agent always just wants to optimize getting rewarded. It wants to optimize rewards. That's all an agent wants. And so the cool thing about agents is they have a decision procedure, and that's going to be some kind of algorithm. And usually it's a variation of a deep neural net, like deep Q learning or convolutional deep Q learning, which we'll talk more about. Sometimes it can be really simple ML algorithm, like Thompson sampling. And what happens is there's a Markov decision process, or MDP, which is just a process that models how the agent interacts with the environment over time. So the agent, you can think of the agent has a neural net, usually, and over time it has, at each time state, it observes the current state of the environment. It decides an action to perform, then it either receives a reward or punishment, and it enters the next time state, keeping track of that reward or punishment, processing it in its neural net as part of its input. The goal of the AI is always the same in reinforcement learning, to maximize accumulated rewards over time. That's the sum of all the rewards received at each transition. So you can think about this as like reinforcement learning is really freeing and the really flexible type of deep learning where the agent's just given a goal and not told how to get to that goal. The weights are left free to adjust based on the input. But what it's trying to predict in this case is what's going to give me the most rewards at any given time point in time. So if I have 50 time slices in a loop, a single iteration, the goal is to maximize the amount of rewards that the agent can get within that time frame. Excuse me. And the neural net will attempt to learn over time by adjusting its weights based on the input, the best course of action at any given time as a kind of prediction. It predicts this, and if the neural net does so rightly, it receives a reward, and that gets put into its system. So that's where I want to get to, because I think that's kind of the coolest part of the real intelligence part of artificial intelligence. Because you do have an independent agent that is learning to navigate its environment, even though it's a digital environment, over time. And we will get there, I promise. Last thing I want to talk about is the philosophical implications of AI. So I will only talk briefly about this, but because it's just such a massive topic, there are some deep philosophical implications in AI. And one of the things is that if we think of the mind as a result of our brain activity, our brain activity, the information flow is modeled in a neural net, right? In an artificial neural net. And we know that in a human brain, that same information flow underlies consciousness and thought, right? And that's a very interesting thought, because the ethical implication of consciousness is that if something's conscious, if something can go well or badly for it, it has rights. We have a right to not cause it unnecessary suffering, and it has a and we can see that in all life, right? That can do things like feel pain. If something can feel pain, and we have a choice whether or not to cause it pain, unnecessary pain, right? Not like a doctor, but like unnecessary. Then we have a moral obligation to not cause it pain and to maybe help its flourishing. Obviously, in machine learning today and artificial intelligence today, deep learning, that's not really a high priority of like thinking, are these machines actually conscious? Do they have rights? But I just want to like bring that up as this is, as we add sophistication, as deep learning gets us better, visual recognition, information processing through neural nets, gets us better object awareness, better, agent reactions and agent learning from the environment. Aren't we getting closer to human consciousness? Aren't we getting closer to the same function that our brain states underlie? And yes, it's in a digital form, but our brain states, at a certain level of description, are electrical activity or not electrical activity. They're electrical excitement neurons, or neurons that aren't electrically excited, right? Binary values. And if we're creating that, I think it's worth thinking very deeply about what consciousness is in our own case, and what we know about the mind and learning in our own case, and what it means to be creating learning minds in the world, right, in the digital space. That's all I really wanted to say. I'll end on that. And so we didn't get to TensorFlow or Keras today, but I'll start with that in a follow-up video and take us through some basic TensorFlow and Keras, and then we'll move on to some reinforcement learning, and that'll be the follow-up sequel to this one. But I wanted everyone to have some basic understanding of what a very basic neural net is and how that might look in just raw Python code without using any external libraries, with a very simple form of data. And then we'll look at some much larger data sets next time, and finally we'll go into Unity's machine learning reinforcement learning agents. So I hope that was helpful to just get your bearing on what machine learning is, what artificial intelligence is, why Python is used so often in this, and it's just become like the main language of machine learning, and it's because of all these APIs and all of the developer work that's going on there. And it also happens to be the language that's used in the Unity ML agents in the back end. So thanks for watching, and stay tuned for the follow-up.